Now that we know how to determine the geometry of a molecule, now we are ready to understand how the polarity of a molecule works. And probably the most important factor here is to determine if you have polar bonds. Because simply put, you will have a polar molecule if you have polar bonds. But that is required, but does not guarantee that you will have a polar molecule. And now we are going to understand why that happens. So a little humor here. Knowing about the molecular polarity is important because polarity, simply put, controls many of the properties of the molecule. Properties such as melting point and boiling point, and which in turn, depending on these values, then you will control the state of that substance, whether it's a solid, a liquid, or a gas. And also because of the polarity, then you will have control, or you will be able to predict how the solubility of a particular substance works. Okay, so in this case it's important to recognize polar bonds in the molecule, and remember, polar bond, it's unequal sharing. This is polarity comes with the covalent bond. Okay, and the covalent bond is sharing of electrons, and when you have a polar bond, is unequal sharing of electrons. And the non-polar bond is when you have even share of electrons. Okay, that will happen when you have identical elements, or our cutoff here is 0.4. And if you are right there at 0.4, well, there are people that will tell you it's non-polar. There are people that say, well, it's slightly polar. You have some room there to work whether it's a polar or non-polar. Okay, so remember, the more electronegative atom in a bond will attract the electrons to itself. Okay, so those electrons will spend more time around that atom. So in this particular case, we have the HCl molecule. There is a difference of electronegativity of 0.9 there. This is a polar molecule. We indicate the polarity of that bond with this arrow. That's a vector. The direction of the arrow points in the direction of the more electronegative atom, and therefore you have a partial negative charge on chlorine and a partial positive charge on hydrogen. Now we can see this also in this way. Okay, the partial negative charge means that the electron density around that atom is larger than in the other atom. So you have a region of high electron density, you will have a region of low electron density, and that corresponds to the partial charges. Now remember, partial negative goes into the more electronegative, the partial positive goes into the less electronegative. But in a molecule you have a more complex situation because you have multiple bonds, right? Well, let me rephrase that. Multiple bonds in the sense that you have more than one bond attached to the central atom. That's what usually happens. So to represent the polarity of a bond, and later on the polarity of a molecule, we are using vectors. And in this case, the direction of the vector indicates where the more electronegative atom is. Now we add the size or the magnitude of that vector, tells you how polar that bond is. The longer the vector, let's write that down, longer vector, that's higher polarity. So the more polar the bond is. Okay, so in this case, between boron and fluorine, you have a longer vector than you would see in carbon hydrogen. Usually a carbon hydrogen bond I would consider non-polar, but we recognize that carbon is a little more electronegative than hydrogen. Okay, so we have talked about this before. I think the dipole moment of a bond, we're gonna keep using that, and this is an equation that we are not really gonna use. We just want to understand that we can refer to the polarity of a bond with the dipole moment. Now, the dipole moment is a way to quantify how polar that bond is. We don't have to worry about this. We are not going to make calculations. I just want you to understand that you can refer to the polarity of a bond and the polarity of a molecule in terms of a dipole moment. So here all we want to know is if you have a dipole moment. This is dipole moment, the micro symbol if you will. This is non-polar. Whether a bond or a molecule, a dipole moment equal to 0 means that is non-polar. Therefore, a dipole moment different from 0, regardless of the value, that is going to be a polar bond or a polar molecule, whatever they are. So anyway, here we are referring to what situations, or in what situations you have a dipole moment equal to 0, in what situation you have non-polar molecules. Well, diatomic molecules of the same element, nitrogen, oxygen, hydrogen, fluorine, chlorine molecules, all of those, because you have the same element, the difference in electronegativity is going to be 0, and the bond is going to be non-polar, the molecule itself is going to be non-polar. That will happen with molecules with that have elements with low difference, small difference in electronegativity. For example, there's difference in electronegativity between carbon and sulfur is small. Nitrogen and chlorine, same thing. So technically you will have non-polar bonds between those atoms. And this is probably not necessarily the most difficult, but it will give you more work to identify whether the polyatomic molecule will have will be polar or non-polar. Okay, here the dipole moment, we are not now referring to that molecular polarity, whether the overall molecule is polar or non-polar. So this is very important. If you have dipole moments that cancel each other, then you will have a non-polar molecule. Okay, so, and this is also very important, right? So whenever you have a molecule and that molecule only have non-polar bonds, okay, non-polar bonds is equal to non-polar molecule, regardless of the shape of the molecule. Okay, there is no way for you to make a molecule polar if it only has non-polar bonds. So non-polar bonds is non-polar molecule no matter what. Now with polar bonds, you could be polar or non-polar. Okay, it could be polar molecule, could be non-polar molecule. It all depends on how the shape of that molecule works. Okay, you have both cases. So having polar bonds does not guarantee you have a polar molecule. So in this case, we have the CO2 molecule. Okay, definitely carbon is less electronegative than hydrogen. You will have those vectors pointing in that direction, but the way the molecule, the shape of this molecule, allows for those two vectors to cancel each other. They are pointing in opposite directions. They are equally strong because it's the same type of bond. It's a carbon-oxygen double bond. They are pointing towards the oxygen. This is a linear molecule, so those vectors cancel each other. Because they are canceling each other, this is a non-polar molecule. Now we have a situation here with a water molecule in which you have those vectors pointing in the direction of oxygen. Okay, this molecule is not linear anymore. This is bent. This is a bent molecule. Those vectors don't have a chance to cancel each other. Therefore, you will have what you see here is the net dipole moment of the molecule is pointing in the direction of the oxygen, still towards the most electronegative atom. So because they don't cancel, then this molecule is a polar molecule. So two cases, you have polar bonds in both molecules, but one is non-polar because those vectors cancel each other, and the other one is polar because you don't have a chance to cancel those vectors with each other. Okay, so another case here, this is carbon tetrachloride, and as such you see 4 electron groups there, so this is tetrahedral. And all the vectors are pointing in the direction of chlorine because chlorine is more electronegative than carbon, and therefore those chlorines are pulling electron density away from carbon. So you have a higher electron density around the chlorine atom than the carbon atom. So you see those negative partial charges on chlorine and a partial positive charge on carbon. Okay. Now this is tetrahedral, and in that configuration, because all the vectors are the same, is the same type of bond, and they are pointing in that direction. It's not like they are not opposite to each other, but the whole structure makes it in such a way that all those four vectors will cancel each other. Now for that to happen in a tetrahedral, they have to be all the same bonds. Here you have CHCl3, which is chloroform of or trichloromethane. It's another name for that. They are not all the same bonds, and carbon is a little more electronegative than hydrogen, so this vector is pointing in that direction. So now the vectors for chlorine don't have the opportunity to cancel each other, because this is pointing in the direction of carbon and the others are pointing away from carbon. So you have a dipole moment that is pointing in that direction. Okay, this is your net dipole. So that molecule is polar. So this is non-polar. This is polar. Okay. So how do we determine overall? How do we do to determine whether a molecule is polar or not? Well, draw your molecular structure. So Lewis, then molecular geometry. Okay, then you're gonna add the arrows, you're gonna add the vectors. Okay, add vectors just to understand in what direction those dipole moments are pointing. Okay, and determine what the resultant is. This might be a little intimidating because it says about analytical geometry and vector addition and all of that, but this is simpler than you think. Okay, because we're gonna have this table. But I'm showing the table. It's not like you're gonna have the table in the exam, correct? So this is showing you what the molecular geometries are, in which some cases in which you can predict what is going on in that molecule. Anything that you don't see here, you can represent that as a combination of this geometry. For example, you don't see here particularly the trigonal bipyramidal or the octahedral, but you can refer to those geometries based on what you see in this table. So notice that on all these cases, the blue arrows, blue is dipole moment for bonds, and red is dipole moment for molecule. Okay, and you see, forget about the red ones for now, but you see that the blue arrows are all pointing away from the center, because that center that you see there, that is your central atom. And a central atom, the central atom usually is the least electronegative atom in the molecule. Therefore, those vectors will point in the direction of the more electronegative, which is going to be the terminal atoms. So that's why you see it in this way. So the important thing here is that when you have a linear, a trigonal planar, or a tetrahedral structure, those vectors have the opportunity to cancel each other if they are all of the same magnitude. That means all bonds have to be identical. Okay, if they are not, they will not have the opportunity to cancel each other. So it is a requirement. If you're gonna have a nonpolar molecule with those geometries, the bonds have to be exactly the same. If not, they don't cancel each other. Okay. Now for the trigonal pyramidal and the bent structure, no matter what you do, no matter what bonds you have, you're going to have a polar molecule if you have polar bonds, because there is not a single chance that you can have those vectors pointing in opposite directions or in such a way that they will cancel each other. So bent and trigonal pyramid, always polar. Remember, always polar if bonds are polar. If the bonds are not polar, no matter what you have, the molecule is going to be non-polar. Okay. So then linear and trigonal, planar, and tetrahedral will be polar if you have different bonds there. So in this particular case, well, nitrogen is more electronegative than hydrogen, and well, you don't have a central atom here that is less electronegative, but it's because hydrogen is a terminal. Okay. Hydrogen always terminal. But this is just to illustrate the point that the vector is going to point in the direction of nitrogen in each one of those cases. So you will have a net dipole moment that is going to point up on the nitrogen. And if you remember, there is a lone pair here. So technically that dipole moment is pointing in the direction of the lone pair. Not because the lone pair is attracting the electrons, but because the when you add all those vectors together, that's the direction in which the resulting vector is pointing. Okay. So last thing to review here, we are back with the methane molecule, and it's a tetrahedral. And in this case, you have a molecule in which all bonds are the same. So in that conformation, if all bonds are the same, they will be pointing in such a way that they will cancel each other. So you have a net dipole moment equal to 0. So it's a non-polar molecule. And we're going to do here is to start adding chlorine atoms. So when you add the first chlorine atom, now the dipole moment for this bond is pointing in that direction. And then you are pointing, all the other ones are pointing in the direction of carbon. And they're smaller because the difference is not, well, it's a little, there is a small difference between the polarity of those bonds, but they are not canceling each other. That's the whole point here. You have a dipole moment different from 0. You keep adding chlorine atoms to this molecule, and then notice that that dipole moment is going in that direction. Is see it as going in between the chlorine atoms. Okay. In the first one, in this one, the dipole moment goes in the direction of chlorine. Now when you have two chlorines, they are competing for electron density, so the dipole moment goes in between the chlorines. If you add one more chlorine, now see like it's going out of that carbon. It's going in between those 3 chlorine atoms. Okay, but still you have 3 carbon chlorine bonds here, and then you have the carbon hydrogen bond there. They are not canceling each other. The interesting thing here is that all these 3 molecules, when you have those numbers of chlorines there, are polar, but when you replace all hydrogen atoms with chlorine, you go back to non-polar. Okay, all bonds are the same in this molecular with this molecular geometry. They will cancel each other, so this is also non-polar. So here the extremes are non-polar, and all these 3 molecules are polar. So it's all about determining in what direction those dipole moments are pointing and whether they cancel each other or not. And then you can determine whether the molecule is polar or non-polar. Okay? So that's it.